So as we get closer to global warming, then we need to start to see how things have evolved differently, especially in the historic period. So we looked at the extinctions that have happened and kind of provided some evidence that human arrival had coincided some of the extinctions of megafauna. As they say, correlation is not causality. So just because the two seem to happen around the same time cannot guarantee us that that was the cause, especially when you go back 10, 15,000 or 50,000 years ago. But we will start to put together as much data as possible, and then in global warming we will introduce a concept called detection and attribution. So you detect a change and then you need to attribute the causes with quite a bit of confidence, because now you will begin to place blame on who did what. So that has to be done much more seriously. So here is one example to start with. This is looking at two separate interglacial periods from the past. The blue one here is an older one, and the red one here is the current one that we came out of the last ice age, and the blue band here is kind of shows the range of values in carbon dioxide and methane coming out of the interglacials. And the idea is to see if our current interglacial evolved similarly to past interglacials. And you can see that CO2 typically during an interglacial would continue to drop coming out of the freezing, because you are going essentially into the next ice age, whereas here you see that it started to drop similar to what we would expect, and then it began to ramp up, coinciding with basically the expansion of agriculture, conversion of forest land into agricultural land, and other human activities. And methane does similar thing, slightly different timing, because it depends on how the swamps were drained, how much rice was being cultivated, how many cattle were being grazed, and so on and so forth. So you can see that both of them go beyond the range of interglacial that we know from the past. That tells you that human impact is in fact beginning to diverge from past climate variabilities, and that begins to tell you that our impact may be real and may be quantifiable. So here, putting together historic evidences, we are looking at the expansion of agriculture, the so-called Fertile Crescent agriculture, which started around the so-called Levant and so on, Syria, Israel, Jordan, etc., just coming out of the glacial around 13 to 10,000 years ago, and slowly over time it expanded into Europe, UK, and so on. Of course, there is an expansion also towards India and China, which is not shown in this map, but we'll come back to other examples of that. So you can see clearly how the agriculture began to expand around the world, and later on to the so-called New World, North America and South America. So here is the example of rice irrigation between 5,000 to 1,000 years ago, and much of India, including Mohenjo-daro, Harappa, going off into the Hindu Kush mountains and so on, all the way into Japan, China, all the way north, and into South Asia and Southeast Asia. All these are in a good monsoon regions, and the rice eating culture now is very strongly established in these regions, and this leads to other issues like how do you adapt to new food types. So if rice cultivating can generate a lot of methane and you want people to reduce the emission of methane, can cultivating rice differently or a different brand of rice be done easily? Turns out that it's not that easy, because culturally once you are attached to, let's say, the white rice or the sticky rice and so on, it's not easy to switch to another type of rice like brown rice or the so-called Madagascar rice or black rice and so on and so forth. Those things have to be kept in mind. So the rice expansion corresponds to the increase in methane going from the beginning of the agricultural era to the present, fairly steady increase, and you can see that this is the expansion of rice cultivating area, and this is the corresponding increase in methane. Again, To remember, methane is in parts per billion by volume, much smaller amounts, and it has much shorter residence times, order 10 years, 12 years compared to carbon dioxide, which is several hundred years. Methane is easily oxidized, but obviously it gets converted to carbon dioxide unless it gets buried and becomes natural gas. Coming back to some of the climate change issues, then, if you look at the Holocene ice core isotopic records, here is the context of the longer term. We came out of the last glacial maximum around 25,000 years ago. Melting started. We had something called oldest Dryas that we didn't talk about. There was an older Dryas, and then there was the so-called younger Dryas. We looked at a bit more in detail, where we said the meltwater from Lake Agassiz was dammed by an ice bridge that had not melted. It melted at some point around 12,000 years ago, released a lot of fresh water into the North Atlantic and perturbed the deepwater formation, thermohaline circulation, and took us back to colder climate before the warming started. And from about 10,000, 11,000 years ago, we have been in the Holocene, and already you can see that the stability of climate here, at least visually, seems much smoother than before, and we will keep coming back to that because we have to put these in the context. Human beings, modern human beings, have lived in mostly in the Holocene. They expanded and exploded in population, science, technology, etc. So, what does that mean in terms of our vulnerability to larger perturbations to climate? So, looking carefully again, 11,000 years ago, increasing temperatures, deglaciation, origin of agriculture happened somewhere around here, and there was several events that are marked here, so called 8.2 kilo year, 8200 kilo year event, 5.9, 4.2, and then of course we will come back to look at the medieval warm period and the little ice age which we have mentioned. So, this is what we are generally calling the historic period, because we have, other than the climate record, ice records, we have some historic archaeological and other evidences, paintings and so on and so forth. So, 8.2 year is somewhat similar to the younger Dryas, much smaller, about half a degree or so change. Again, it is related to post-glacial lakes releasing freshwater flux into the North Atlantic, perturbing the Atlantic meridional overturning circulation that is linked to the global meridional overturning circulation. And there was periods of drought around 5.9 kilo year, which goes back to the perturbations to the Sumerian culture. And then you had a fairly mild climate for a few thousand years, which is referred to as the climatic optimum. So, we will look at the expansions of civilization, especially the greening of North Africa, where the Sahara Desert is now, and how the civilizations of the time expanded, and then when the drying resumed, they all shrunk back to the Nile Delta from where they started. So, you can keep on looking at human history, and you will always find, we mentioned the Maya civilization, for example, or Incas. It somehow always relates to water. When water is available, there are new settlements, they expand quickly, and when there are extended droughts that continue for years or decades, then the civilizations either go extinct or they have to migrate somewhere. And this continues even now. If you look at what is happening around Syria and Sudan and Somalia and other places which are dry, there are still many conflicts that can be related to droughts and water issues. In countries like India or US or Europe, these water battles are between states, there are agreements and so on, but the question is how much of a perturbation can civilizations tolerate without getting into deeper conflicts. That's always something to remember in terms of global warming impacts or climate change impacts on human civilizations. 4.2 kilo year corresponds to, again, collapse of some of the old world empires, including our region, Mohenjo-daro, Harappa and so on. And medieval warm period, we will see, corresponds to, for example, the most striking example of that is the Greenland ice melting providing enough agricultural land, and the Vikings going and settling on Greenland, and when the cooling started and little ice age came, they had to go back or they disappeared. So, we will see that a little bit more. So, this begins to give you a sense of all the origins of New Eastern civilizations in Sumeria, the Bronze Age, this is the Greenland ice core, the Iron Age, classical Greece, Greco-Roman ages, and here we are with the Industrial Revolution. So, we have to keep in context not only this 50 million year cooling we were in, but this secular cooling coming out of the last ice age, and the global warming is now happening on top of that. So, it is always a question of whether in a natural climate variability we would be heading towards the next ice age, because we are still in this cycle of 100,000 years ice ages and interglacials, and if global warming somehow changed that. So, we are definitely coming out of the colder climates, but global warming is kind of accelerating the warming. I like this figure because it shows much more clearly that the temperature perturbations during the Holocene were fairly small. Here it is about 1 degree, less than a degree, half a degree, and so on, but each of these perturbations have had huge impacts on civilizations at that time. So, what does that mean in terms of global warming? We are now about 1 degree centigrade above the temperature we started with at the pre-industrial time scale, and we will see that global warming debate is focused on trying to limit greenhouse gases so that we do not cross 2 degree centigrade warming compared to the pre-industrial. It is pretty clear that we might end up crossing that unless some game changer comes along and starts pulling carbon dioxide out of the air and so on, or we change our ways very rapidly and stop emitting carbon dioxide. Nonetheless, the question is of great interest is what are the kind of global temperature ranges, perturbations that societies can tolerate without having large scale catastrophes. Does science and technology we have now in terms of buildings and infrastructure and so on protect us from larger and larger perturbations? If you look at examples of even hurricanes hitting rich countries like US or Puerto Rico or poor countries, island states and so on, you have to learn from those examples to see really how resilient we are to natural perturbations, or natural perturbations getting much worse with global warming. Those are the kind of questions we will keep on coming back to. This is just another figure showing more clearly when agriculture emerged, when Mesopotamia was flourishing, where the climatic optimum was, where the Vikings occupied Greenland during the medieval warming. Again, look at the range. And why is this important? Because this one has now added global warming to it. Okay? So, we started warming, and in 100 years we expect to continue in this range. So, this gives you a context of what have been the perturbations during the Holocene, during which we mostly came to dominate the planet, and what are the perturbations we are creating because of our own greenhouse gas emissions, land use change, agriculture, urbanization, and so on and so forth. So, these are kind of the projections, and the projections then always try to look at what are the limits from the past that we can learn from that could be catastrophic, not just for us, but many of the species that are living on the planet along with us. Many have disappeared, but there are still many that we would like to preserve, and what are the kind of tolerances we have. So, even the so called little ice age, which was partially global, is not completely global. It was focused much more on the European region than elsewhere, but look at the cooling. It is fairly small, barely 1 degree centigrade, but it had large scale impact. So, it is always looking at the past climate variability and change to understand how historical period has been affected by these changes. To put it even in a longer context, let us go back to 500 million years where we said the Cambrian explosion happened. So, this is the post-Cambrian coming out of the previous era, the pre-Cambrian, and obviously evolution of many new species here, up to 25 million, evolution of plants, evolution of ice. There were some ice ages after plants evolved, CO2 was drawn down, Carboniferous where a lot of the organic matter was buried, and so on and so forth. Then we talked more carefully about the last 50 million years where we have been cooling, where the Himalayas, the monsoons, increased erosion and so on played a role. And we went from this obliquity cycle of 41,000 years to more of a eccentricity cycle of 100,000 years. So hominins began to evolve around here, and human beings basically evolved, Homo sapiens basically evolved around here. We looked at this more carefully, the last glacial maximum. So in this context, you can see Holocene is here, the scales are different here. These are millions of years, thousands of years, hundreds of years, 5,000, 10,000 here, you are going hundreds of thousands of years. Nonetheless, you can see again global warming is much more rapid than the fastest warming signal we have seen in the past. So, the so called Paleocene Eocene thermal maximum. The scale here is millions of years. So, this happened on a much longer time scale than the warming that is happening here. That gives you a context, but it also tells you that the climate in the past has been very warm. When the dinosaurs were around here, the Arctic had no ice, Antarctic had no ice, there were lush forests in Siberia, mammoths and dinosaurs were wandering around in the Arctic Circle, and this is one of the reasons why many of the energy companies are interested in the Arctic ice melting, because a lot of photosynthesis that happened there during these times has buried a lot of oil and gas. So, oil companies will be happy to go there and dig for oil and gas, right. So, those are the kind of issues. So, the question somebody can ask you is, if temperature has been so much warmer in the past, why should we worry about this warming that is still so much smaller than the past warmings? Obviously, because we have mostly evolved in this time scale, there were no human beings here. Our ancestors evolved here and many of them went extinct. So, we are the only ones remaining. So, what kind of temperature tolerance do we have? What kind of climatic changes can we tolerate? That is always the interesting question. Coming back now to our historic period, this is showing the civilizations from 9,000 to 8,500 years ago, down to 7,000, 3,000, 3,500 years. So, coming out of the Younger Dryas, North Africa was like it is today, it was dry and it was a desert. So, all the civilizations that were around were huddled together on the Nile. Okay. As climate change happened, this is related to orbital forcing as well. The ITCZ, or the Intertropical Convergence Zone, shifted and brought widespread greening and more water. The lakes got filled and so on in North Africa. And as soon as that happens, you can see that the civilizations basically spread out over large parts of Africa. And as the wet period ended and began to get dry again, slowly the civilizations moved back, or some of them remained further south. There is still some wetness and possibility of agriculture over there. Some tribes survive around remaining little water bodies, but now even over the 20th century, you can look at things like water bodies like Lake Chad and so on. They have had massive changes in the last 100 to 200 years, which includes the impacts of climate change, global warming, but also increases in population and so on. So, this is a good examples of how civilizations chase water, and then not everybody can chase back to the original source of water. Many will go extinct, many will simply disappear, many will maybe innovate, and there is some evidence that the Mohenjo-daro Harappa region, which had kind of, this is showing the monsoon rainfall going back to the last glacial maximum, and there were drier periods the same time as when North Africa was drier. Then we got in a wetter period. So, here two rainfalls are shown, just the summer monsoon period and the whole year. So, depending on where you are, you can get substantial northeast monsoon or winter monsoon as well. So, the total annual rainfall can be much higher. Nonetheless, you can see that during the wet periods, the Mohenjo-daro Harappa civilizations over the Indus Valley got established. They survived for quite a bit, and then a very steep dry period arrived and the civilization disappeared. There is evidence that they tried to build structures to do water harvesting and so on. So, if you go to places like Machu Picchu or even parts of Hampi and Mohenjo-daro Harappa regions, archaeologists find evidences that there were efforts to pipe water, save water, build structures to harvest water during rainy seasons and save it for the dry period. In Machu Picchu, there are even structures that could harvest fog, because it's very high in the mountain, there is not much rain, but depending on the wet period or dry period, there can be more humidity and fog, so they could harvest fog. So, civilizations tried to invent, even the Romans had built aqueducts and so on. So, water has always been part of the theme, and under global warming, water is a big theme. So, we will see that a little bit later on. So, these are kind of historical evidences of how climate change, water availability affected civilizations pretty seriously. So, just like global warming, then historic periods, we have to start looking at why climate changed from the Holocene optimum to medieval warming to the Little Ice Age to where we are now. And it turns out that you can look at the solar forcing. This is the change in total solar irradiance, multiple constructions. So, as you go back in time, you have to create some kind of a so-called sun model, solar model, or a heliophysics model that allows you to reconstruct changes in radiation. This one is way out compared to the other models, but nonetheless, there are these changes over the historical period, just going back to the last 1000 years. Long story short, it turns out that solar radiation may have contributed a little bit, but it's not a dominant forcing at any time scale, not in the historic period, and turns out not even in the global warming period. We will look more carefully at the solar radiations for the 20th century. That's not the perturbation due to changes in sun's radiation is not a contributor to trends or global warming kind of things, but it does create kind of a 10-year, 11-year cycle in the monsoon, for example. So, there are many sunspot cycles that we will come back to a little bit later on. But what has played a bigger role in initiating the cooling, for example, coming out of the medieval warm period into the Little Ice Age, is the volcanic forcing. So, you can see that volcanic forcing can create large perturbation, even though it lasts for a very short time. It's a pulse, because volcanoes erupt typically and then they die down. But there are two things. One, the amount of dust produced by the volcano obviously matters. Secondly, it matters where that dust is put in. So, remember we looked at the profile of temperature in the atmosphere. It looked like this: troposphere cools as you go up to the tropopause, and then the stratosphere warmed. The one detail that we didn't point out there is that if you go from the equator to the pole, then the tropopause height actually drops, which means the temperature will be like this here, and so on. So, if there is a volcano in Iceland which is at high latitude, that volcano can easily put more dust into the stratosphere than a volcano in Indonesia which is sitting in the tropics. So, the volcano in the tropics has to be much more powerful to reach the stratosphere, whereas the volcano in Iceland can easily get into the stratosphere. Why is it important to get into the stratosphere? Basically, in the stratosphere, stratus means stratified. It is stable because it warms as you go up. So, cold is heavier air, warm is lighter air. So, it is nice and stable region. So, you do not have a lot of weather in the stratosphere. So if you put stuff in the stratosphere, it can stay there for a long time. So if you dump a lot of ash and aerosols into the stratosphere through a volcanic mechanism, it can spread horizontally for a long time and stay there for a long time. So it can affect climate for many years. Okay, and there are many evidences. We'll see the temperature effect in a little bit. So even though volcano is a pulse, it can create perturbations, and when you have increased activity like this, for example, see there is hardly any volcanic activity here, suddenly there are lots of volcanoes coming into the 12th and 13th centuries. This is one of the reasons why the medieval warm period began to end and the cooling into the little ice age started. It was a lot of this volcanic forcing. Volcanoes block the sunlight, cool the global climate. That's what happened. So we have had some elevated activity also, Tambora, Krakatoa and so on. So a lot of stories, Edward Munch's famous painting, The Scream, the things like Year Without Summer, where the volcanic ashes made the summer so cold that crops failed and so on over Europe. And there were stories written like Frankenstein and so on, which came out of writers like Mary Shelley taking a bet and saying they were going to sit and write horror stories when this Year Without Summer happened, etc. So volcanoes are a big forcing and they are natural forcing. Why are they forcing? Because they can perturb radiation balance at the top of the atmosphere. This is what can change climate. So here we are looking at a little bit of details of how the Vikings started from various places in Europe. Their times are written here. This is circa 870, 860, 800 and so on. They obviously colonized Iceland, so Iceland is still habited by human beings. The Vikings settled in this little southwestern corner and built structures, agriculture, they had settlements and so on. So they survived for a while, and Eric the Red is the famous Viking. His son Leif Erikson went all the way into northern part, and there is evidence that he made it all the way to Newfoundland. So this is well before Christopher Columbus made it to the Northern America and established the colonies and then eventually became America and so on and so forth. So this is almost 500 years before. But as climate began to cool because of volcanic eruptions and so on, as the medieval warm period came to an end, the Greenland ice began to grow and this place became unsuitable for agriculture, and then Vikings disappeared. Very clear example of how climate change influenced the historic period. The Mayas were up here in Central America, Mexico and so on, whereas in South America you had other empires like the Wari Empire and the Tiwanaku and so on, which spanned various periods. And we will see when we do El Nino that in this region, remember, there is upwelling and there is very cold water here, Galapagos somewhere here. So this entire coast is cold because the winds that are blowing this way and this way will push the water away from the coast and cold water will come up. Cold water is good, a lot of phytoplankton, which means a lot of fish, but it also means cold air and no rain. So these are very dry regions, except when El Nino comes and warm water comes, they can have so much rain that it can flood and mudslides and so on. But if the El Nino only happens 2 to 7 years and by some change El Nino didn't happen for a long time, then essentially you can have very dry periods here, and such dry periods, extended droughts did occur and these civilizations disappeared. But you can see that that also kind of coincides with the time when volcanic activity began to increase. So that cooling created by volcanic forcing probably was global, not just affect the Vikings, but also in the southern hemisphere, cultures like the Mayas, Incas, Wari empires, Tiwanaku empires and so on. So what happened in the Little Ice Age? This period has tremendous amount of historic information. So this is a painting from that time from Netherlands. Netherlands even now in the winter can have many canals which are frozen, and the whole country will be out skiing. With global warming, the freezing of the canals is actually decreasing, and they are very worried. And Netherlands is very close to sea level, so they are also worried about sea level rise and so on. But during the Ice Age, the Little Ice Age, they did have extensive freezing, and there were several wars, there were famines. Every time you have cold temperatures, you're going to have drier climate, you're going to have crop failures, you're going to have more dust, and so on. So there were great famines, the Black Death. So when you have a famine, rats can get closer to human beings looking for food. So you can get things like plague, and this happens even now during an El Nino, places where it gets more dry, or during a La Nina, the mice that tend to live in the farms where they can find food tend to come into human habitation and spread diseases, because they get into the grains you have stored and defecate and so on and so forth. So things like Manchu conquest of China, the rise of potatoes as way to deal with famine, the French Revolution, books like Frankenstein, the invention of bicycle, and the Year Without Summer. Year Without Summer, as I said, is related to volcanic forcing, but volcanic forcing was one of the causes for the Little Ice Age. So there are many details. You can Google and find lots of information on the Little Ice Age, how England used to grow good wine because of the climate was different and more favorable to wine. Now they are growing more hops and making good beer instead of wine. French make now good wine, and so on and so forth. So all these things were related to the Little Ice Age. So how did we come out of the Little Ice Age? This is related to two things. One, the volcanic forcing seems to have died down, so there is quietening off. So looks like there is a bit more volcanic activity here than here or here. That could be a contribution. But the other more interesting theory, of course, is that industrial revolution and global warming started around the same time. So the evidences of the end of the Little Ice Age are locked into many places, like the glaciers in the Andes, the Himalayas, the Alps. So the Argentiere Glacier picture shows here the same picture. You cannot see probably, but the glacier is all the way down to this building here. The same building is still here, and you can see that now the glacier is way up there. All this part is now cleared of glaciers. Okay. There are many theories. For example, if there is a lot of pollution from coal burning or traffic or other kinds of emissions from trains and so on, that can get into the ice and snow. And if you have black particles in ice and snow, they can absorb heat and they can melt the ice and snow faster. So the places like some mountain passes in Himalayas, the traffic has gone up so much that they can find huge amounts of pollution in Himalayan glaciers, for example. And now we have fairly good data to argue that potentially the increased black carbon or soot in the glaciers and snows can accelerate the melting rate. So beginning of industrial revolution produced a lot of pollution because we were relying heavily on coal. Was that part of the story, or was it the increase of the temperature alone? Was it the end of the volcanic cooling and so on? Could be combination of all of them, right? So in 100 years you have substantially decreased the glacier extent, and this is a universal phenomena, as we will see, with some exceptions because of local climate responses and so on. The other solar variability, so we said solar variability could be because of the strengths in solar fusion activities themselves, or there are knots that get formed and that create black spots, and they are called sunspots. The critical thing to remember here is that when a sunspot forms, around it a bright region called plage forms. Plage in French means beach. So it's like a beach around a black dot. So actually radiation goes up. So more the sunspots, more the radiation that will come, which means if you have minimum in sunspot activity, then the radiation will be actually less. So you will get signatures in C14 because the production of C14 changes. So they were coming out of the medieval warm period. Somewhere here you began to have several minima in solar activity like Wood minimum, Wolf minimum, Sporer, Maunder minimum, and so on, and then we got into modern maximum. Again, as I said, these probably contributed to the Little Ice Age, but the perturbations due to these radiative forcings are too small, especially as you come here. Many people in the beginning were arguing that maybe solar activity is causing global warming, but now we have good satellite measurements of radiation, and it turns out that they are not major contributors to either cooling or warming, but they can of course add a little bit to the cooling that's being driven by volcanic activity and so on. So sunspots can increase the radiation because there is brighter plage around a sunspot. So more the sunspots, more the energy, less the sunspots, less the energy. That's what you have to remember. And when you change the sun's energy, amount of production of C14 and beryllium changes, which will be recorded. So this is showing the sea ice in Icelandic region coming out of the medieval warm period began to increase and then went up quite a bit. Again, ice albedo feedback would have kicked in. More ice means more reflectivity, more albedo, less energy being absorbed, cooler temperatures further increase the freezing. And one thing that's worth repeating is that Little Ice Age was not really global in extent. There are evidences that this cooling happened, but maybe it was mostly restricted to the northern hemisphere, more heavily focused on the North Atlantic European region. Okay. So the other things we have to start looking at is the human impacts. How have humans affected? Remember we looked at the carbon dioxide and methane changes and said that 5,000–6,000 years ago the carbon dioxide and methane started going in the wrong direction compared to previous deglaciation periods. So the clearing of forests for agricultural activities started with the advent of agriculture and the expansion of this fertile crescent and so on, but reconstructing past clearances is not always easy. Various evidences are used to see what the vegetation cover was and how it has changed, and you can see that the two estimates here by Hyde and Kaplan, they are very different. So this is some kind of a population model that uses the assumptions of how population affects forest clearing, while the second estimate is based on historic evidence indicating much larger clearance. So dramatic differences in the estimates of the clearance. Obviously this will change the CO2 emission rates, global warming rates and so on. So we will keep on looking at the evidences, we will keep on saying what the uncertainties are, but we have to keep on also moving towards the current century, and eventually we will come back to India specific impacts and what are the global warming projections, what actions we can take to avoid global warming. So we will come back and continue this historic climate discussion in the next lecture. See you later.